An axiom or postulate as defined in classic philosophy, is a statement that is so evident or well established that it is accepted without controversy or question. Thus, the axiom can be used as the premise or starting point for further reasoning or arguments. Usually in logic or in mathematics, the word comes from the Greek ἀξίωμα, that which is thought worthy or fit, or that which commends itself as evident, as used in modern logic. An axiom is simply a premise or starting point for reasoning. Whether it is meaningful for an axiom, or any mathematical statement, to be true, is a central question in the philosophy of mathematics, with modern mathematicians holding a multitude of different opinions. As used in mathematics, the term axiom is used in two related but distinguishable senses: logical axioms and non-logical axioms. Logical axioms are usually statements that are taken to be true within the system of logic they define implies a, while non-logical axioms are actually substantive assertions about the elements of the domain of a specific mathematical theory. When used in the latter sense, axiom, postulate, and assumption may be used interchangeably. As modern mathematics admits multiple, equally true, systems of logic, precisely the same thing must be said for logical axioms. They both define and are specific to the particular system of logic that is being invoked. To axiomatize a system of knowledge is to show that its claims can be derived from a small, well-understood set of sentences. There are typically multiple ways to axiomatize a given mathematical domain. In both senses, an axiom is any mathematical statement that serves as a starting point from which other statements are logically derived. Within the system they define, axioms cannot be derived by principles of deduction, nor are they demonstrable by mathematical proofs. Simply because they are starting points, there is nothing else from which they logically follow, otherwise they would be classified as theorems. However, an axiom in one system may be a theorem in another, and vice versa. Etymology. The word axiom comes from the Greek word chi iota omega mu alpha, a verbal noun from the verb chi iota omicron epsilon iota nu, meaning to deem worthy, but also to require, which in turn comes from chi iota omicron sigma, meaning being in balance, and hence having value, worthy, proper. Among the ancient Greek philosophers, an axiom was a claim which could be seen to be true without any need for proof. The root meaning of the word postulate is to demand. For instance, Euclid demands of us that we agree that some things can be done, e.g., any two points can be joined by a straight line, etc. Ancient geometers maintained some distinction between axioms and postulates. While commenting Euclid's books, Proclus remarks that Geminus held that this fourth postulate should not be classed as a postulate but as an axiom, since it does not, like the first three postulates, assert the possibility of some construction but expresses an essential property. Boethius translated postulate as petitia and called the axioms notiones communes, but in later manuscripts this usage was not always strictly kept. Historical development. Early Greeks, the logico-deductive method whereby conclusions follow from premises through the application of sound arguments, was developed by the ancient Greeks, and has become the core principle of modern mathematics. Tautologies excluded. Nothing can be deduced if nothing is assumed. Axioms and postulates are the basic assumptions underlying a given body of deductive knowledge. They are accepted without demonstration. All other assertions must be proven with the aid of these basic assumptions. However, the interpretation of mathematical knowledge has changed from ancient times to the modern, and consequently the terms axiom and postulate hold a slightly different meaning for the present-day mathematician than they did for Aristotle and Euclid. The ancient Greeks considered geometry as just one of several sciences, and held the theorems of geometry on par with scientific facts. As such, they developed and used the logico-deductive method as a means of avoiding error, and for structuring and communicating knowledge. Aristotle's posterior analytics is a definitive exposition of the classical view. An axiom, in classical terminology, referred to a self-evident assumption common to many branches of science. A good example would be the assertion that when an equal amount is taken from equals, an equal amount results. At the foundation of the various sciences lay certain additional hypotheses which were accepted without proof. Such a hypothesis was termed a postulate. While the axioms were common to many sciences, the postulates of each particular science were different. Their validity had to be established by means of real-world experience. Indeed, Aristotle warns that the content of a science cannot be successfully communicated if the learner is in doubt about the truth of the postulates. The classical approach is well illustrated by Euclid's Elements, where a list of postulates is given, followed by a list of common notions. Postulates: it is possible to draw a straight line from any point to any other point. It is possible to extend a line segment continuously in both directions. It is possible to describe a circle with any center and any radius. It is true that all right angles are equal to one another. It is true that, if a straight line falling on two straight lines make the interior angles on the same side less than two right angles, the two straight lines, if produced indefinitely, intersect on that side on which are the angles less than the two right angles. Common notions: things which are equal to the same thing are also equal to one another. If equals are added to equals, the wholes are equal. If equals are subtracted from equals, the remainders are equal. Things which coincide with one another are equal to one another. The whole is greater than the part. Modern development: a lesson learned by mathematics in the last 150 years is that it is useful to strip the meaning away from the mathematical assertions and definitions. One must concede the need for primitive notions, or undefined terms or concepts, in any study. Such abstraction or formalization makes mathematical knowledge more general, capable of multiple different meanings, and therefore useful in multiple contexts. Alessandro Padua, Mario Pieri, and Giuseppe Pino were pioneers in this movement. Structuralist mathematics goes further, and develops theories and axioms without any particular application in mind. The distinction between an axiom and a postulate disappears. The postulates of Euclid are profitably motivated by saying that they lead to a great wealth of geometric facts. The truth of these complicated facts rests on the acceptance of the basic hypotheses. However, by throwing out Euclid's fifth postulate we get theories that have meaning in wider contexts, hyperbolic geometry for example. We must simply be prepared to use labels like line and parallel with greater flexibility. The development of hyperbolic geometry taught mathematicians that postulates should be regarded as purely formal statements, and not as facts based on experience. When mathematicians employ the field axioms, the intentions are even more abstract. The propositions of field theory do not concern any one particular application. The mathematician now works in complete abstraction. There are many examples of fields. Field theory gives correct knowledge about them all. It is not correct to say that the axioms of field theory are propositions that are regarded as true without proof. Rather, the field axioms are a set of constraints. If any given system of addition and multiplication satisfies these constraints, then one is in a position to instantly know a great deal of extra information about this system. Modern mathematics formalizes its foundations to such an extent that mathematical theories can be regarded as mathematical objects, and mathematics itself can be regarded as a branch of logic. Frege, Russell, Poincaré, Hilbert, and Gödel are some of the key figures in this development. In the modern understanding, a set of axioms is any collection of formally stated assertions from which other formally stated assertions follow by the application of certain well-defined rules. In this view, logic becomes just another formal system. A set of axioms should be consistent. It should be impossible to derive a contradiction from the axiom. A set of axioms should also be non-redundant. An assertion that can be deduced from other axioms need not be regarded as an axiom. It was the early hope of modern logicians that various branches of mathematics, perhaps all of mathematics, could be derived from a consistent collection of basic axioms. An early success of the formalist program was Hilbert's formalization of Euclidean geometry, and the related demonstration of the consistency of those axioms. In a wider context, there was an attempt to base all of mathematics on Cantor's set theory. Here the emergence of Russell's paradox and similar antinomies of naive set theory raised the possibility that any such system could turn out to be inconsistent. The formalist project suffered a decisive setback, when in 1931 Gödel showed that it is possible for any sufficiently large set of axioms to construct a statement whose truth is independent of that set of axioms. As a corollary, Gödel proved that the consistency of a theory like Peano arithmetic is an unprovable assertion within the scope of that theory. It is reasonable to believe in the consistency of Peano arithmetic because it is satisfied by the system of natural numbers, an infinite but intuitively accessible formal system. However, at present, there is no known way of demonstrating the consistency of the modern Zermelo-Fraenkel axioms for set theory. Furthermore, using techniques of forcing, one can show that the continuum hypothesis is independent of the Zermelo-Fraenkel axioms. Thus, even this very general set of axioms cannot be regarded as the definitive foundation for mathematics. Other sciences' axioms play a key role not only in mathematics, but also in other sciences, notably in theoretical physics. In particular, the monumental work of Isaac Newton is essentially based on Euclid's axioms, augmented by a postulate on the non-relation of space-time and the physics taking place in it at any moment. In 1905, Newton's axioms were replaced by those of Albert Einstein's special relativity, and later on by those of general relativity. Another paper of Albert Einstein and co-workers, almost immediately contradicted by Niels Bohr, concerned the interpretation of quantum mechanics. This was in 1935. According to Bohr, this new theory should be probabilistic, whereas according to Einstein it should be deterministic. Notably, the underlying quantum mechanical theory, i.e., the set of theorems derived by it, seemed to be identical. Einstein even assumed that it would be sufficient to add to quantum mechanics hidden variables to enforce determinism. However, 30 years later, in 1964, John Bell found a theorem involving complicated optical correlations, which yielded measurably different results using Einstein's axioms compared to using Bohr's axioms. And it took roughly another 20 years until an experiment of Alan Aspect got results in favor of Bohr's axioms, not Einstein's. As a consequence, it is not necessary to explicitly cite Einstein's axioms, the more so since they concern subtle points on the reality and locality of experiments. Regardless, the role of axioms in mathematics and in the above-mentioned sciences is different. In mathematics, one neither proves nor disproves an axiom for a set of theorems. The point is simply that in the conceptual realm identified by the axioms, the theorems logically follow. In contrast, in physics, a comparison with experiments always makes sense, since a falsified physical theory needs modification.